Okay, NH3. My Lewis dot structure is right here, and I did this by having N as the central atom because H can't be the central atom ever, so that just leaves N. And then I have 3 H's connected to it because there are 3 H's and NH3, and so you connect them with a single bond. And well, first when you start off, you add the amount of valence electrons in NH3, so that would be 8 because N has 5 valence electrons and H has 1, and 1 times 3 is 3. 3 plus 5 is 8, so there's 8. And then when you add the 3 H's over here, you subtract 6 from that because there are 2 bonds going on between here because there's between there and there and there and there. And so you'll subtract 6 to keep track of the number of electrons. And so that leaves 2. And since you have to end up with 0, you need to add 2 more. So you get the pair right here. And that's how you do the Lewis dot structure. And then AX3. A is for the central atom, so there's one of those. And then X is for the amount of outer atoms, so there's 3. And then E is for the amount of the pairs, and there's only one of those pairs, so that's E. And then electron pair shape is tetrahedral right here because that is like the thing as a whole, like bonding and non-bonding, so you don't take into account the pairs when you do that. And so that would be tetrahedral, which looks like that as shown by the drawing there. And the molecular shape, since that includes the pairs, that is trigonal pyramidal, which looks like that with the 3 atoms and then the pair, which looks like this in that model, with the 3 H's, the pair there, and the nitrogen. And then the angle of this thing is a little less than 109.5 degrees because it has the pair, so that makes it a little bit less. Okay, now the polarity for each bond is all of the H's are being pulled out because they're partial positives, and then nitrogen is a partial negative, so they're all being pulled out, and N is right there. Okay, and then this the polarity of the molecule as a whole is polar because the dipole moments don't cancel out. So what I mean by that is you have the model here, and they're all pulling out like away from the central atom, but they don't cancel each other out. Like they're pulling this a certain way, they're like pulling it down. They don't like if there was just 2 that were a straight line, they would pull each other, so it would cancel out, and so that'd be nonpolar. But since these don't cancel each other out when they're pulling, it is polar. Hybrid orbitals. This right there is the hybrid orbital. It is sp3. I got this because you add together the amount of X's and the amount of E's, so that's 4, and then you disperse that amongst S, P, and D on the periodic table. And since S only has 1 pair, you subtract 1 from 4, so you get 3. And then P has 3 pairs, so you subtract the 3 from the 3 and you get 0. And then there are 3 sigma bonds because and there's no pi bonds because pi bonds are double bonds, and I don't have any double bonds. There's only single bonds, and single bonds are sigma bonds, so there's 3 of those, so there's 3 sigma bonds. And then this is a hydrogen bond because there's hydrogen in it, so it makes it a hydrogen bond. And this is covalent because we are all doing covalent ones. Okay, now formal charge. So the formal charge of nitrogen is 0. I got this because there are 5 valence electrons minus these 3 bonds, and then minus these 2 bonds right here for 1 pair. So that's 0. And then for each hydrogen, it's the same. It's also 0 because there's 1 valence electron for hydrogen, and then each of them only has 1 bond. So 1 minus 1 is 0 for all of them. Resonance bonds. There's no resonance bonds because those are when you take away the dots from over here and you create a double bond. But I don't have to do that, so there's no resonance bonds. And this is a complete octet because the bonds add up to 8 because there's 1, 2, 3, 4, 5, 6, 7, 8 because you count each of these twice because there's 2 bonds there. And then the bond order is single between, is 1 because it's a single bond between an H. So there's NH3. Okay, so SF6. The Lewis dot structure is right there, and I did this by first I added all the valence electrons, and so S sulfur has 6 valence electrons, and then fluorine has 7, and 7 times 6 plus 6 is 48. And so that's how many valence electrons you start out with. And then the central atom is S because that is the least electronegative. And so then you do all the bonds for F, and so there will be 6. And 6 times 2 because there's 2 bonds for each thing is 12. So 48 minus 12 is 36. So there's 36 electrons right now. And then you need to complete the octets for each of these, so that you add 6 dots for each one because it's 6 and then 7, 8 for each thing. And then you need to keep track of the electrons still, so you do 6 times 6, which is 36, and so you had 36, so 36 minus 36 is 0, so you don't have to worry about any lone pairs or anything like that. And then this is AX6 because A is for the central atom, and then X is for the number of bonds, or like the number of bonds, and that's 6, so it's AX6. And then the electron pair shape and the molecular shape are the same thing because there's no lone pairs, so you don't have to worry about the non-bonding and non-bonding atoms. So those are both octahedral. So that's shown there in that drawing. And then the bond angle is 90 degrees because that's the bond angle for octahedrals. Okay, so the polarity for each bond, all the F's are pulling out because they're partial negatives. So they're pulling towards the F's. So there's arrows pointing towards F's. And then S has a partial positive thing. So that's the polarity for each individual bond. And for the molecule as a whole, it's non-polar because since all of these are pulling out, it evens out because they're evenly dispersed among the things, so it pulls out. So it's like if I'm pulling on this poster board, but if I pull out the same place and the same strength, then it stays still. But if I pull like a lot over here, then it pulls over here. But since they're all the same, it pulls and it stays still, so it's nonpolar. And so now for the hybrid orbitals, it is sp3d2, and you get this by adding together the x and the e, but since there's no e, you just add together the x with the x, so it's just x, and that is 6. And so you have 6, and you need to disperse it amongst S, P, and D on the periodic table. And since S only has one pair, you subtract 1 from 6 and you get 5. And then P has 3 pairs, so you subtract 3 from 5 and you get 2. And then the last 2 that you have, you disperse them on D, and so there's 2 for D, so it's sp3d2. And there are 6 sigma bonds because they are all single bonds here, and their sigma bonds are the single bonds, and there's no pi bonds, which are the double bonds, because there's no double bonds there. And then this is a London dispersion bond, because it can't be any of the others. Like, it can't be hydrogen, it can't be dipole, it can't be any of those. So that just leaves London dispersion. And this is a covalent bond because all of the ones that we're doing food projects are covalent bonds. There's no other option. And now the formal charge. Since there's 6 valence electrons in sulfur, and you subtract the 6 bonds, you get 0, so the formal charge of sulfur is 0, and the formal charge of fluorine is also 0, because there is 7 valence electrons in fluorine, and then you subtract 1 for this one bond right here, and then you subtract 6 from the 6 for each of these bonds here with the circles, and so that leaves you with 0, so the formal charge of fluorine is 0. And there are no resonance bonds because those are like the double bonds, so I didn't have to do any of that, so there's no resonance bonds. And this is an expanded octet because when you add the number of bonds, there's more than 8, so it's expanded. And then there's a single bond. The bond order is 1 because there's a single between S and F, so there's just 1. And there we go.